Hello everyone. So, am I audible? Can you just write it in chat box or unmute yourself and speaker? Okay. So, I think I will wait for 5 more minutes. So right now it is around 7. So we will wait till 7 5 p.m. Then I can start my discussion. So it's 7:05 and I think we can start. So welcome to this first session. I am Rahul Patel from Chemical Engineering Department, IIT Bombay. So the purpose of this session is to solve the previous year GATE questions and to clarify the doubts related to this question. So what we will be doing is we will be looking into the past year GATE questions for this chemical engineering subject, and we will be going it from by topic wise. So let's say we will look at heat transfer, then process control, and we will be solving the past year questions, and we will be explaining the concepts that are needed to solve these questions. So after this session, we will be having a bunch of questions that have been solved, and then these videos you can access later on from our NPTEL GATE portal. So I think you must be knowing about the NPTEL GATE portal. I'm just sharing my screen and showing it to you all. So this is the GATE portal, which is developed under the NPTEL project. So from here you can see, so this is basically a GATE preparation platform where we have this concepts and video solution of the past year questions, and we will be also coming up with practice tests very soon. So this is the GATE syllabus mapping. So for various disciplines, let's say for civil engineering, you will get this subject wise topics which are basically linked to this NPTEL course videos. So right now we don't have this GATE syllabus mapping for chemical engineering department, but we are working on it and it will be available very soon. Similarly, so this GATE syllabus mapping will help you to understand the concepts related to the GATE paper. Then we have this video solutions. Again, in video solutions, if you click on any subject, then you can select year wise or topic wise. If you have selected year, then you can select again the session, and then you will get the video solutions of each of these questions. So what we will be doing is we will be recording these videos and playing it on this interacting session that we are having right now, and later on this video you can access it from this portal. Also, if you have any doubts related to these questions, then we can discuss it during this session. So yes, so can I get, so yes, can each of you unmute and just say a little about yourself? So what is your background and what are your expectations from this interactive session so that we can deliver a better thing to you? So maybe one by one you can unmute yourself and talk about with yourself.
Sir, good evening, sir.
Yes, so
Sir, I'm Logesh, sir. I'm from Tamil Nadu, Chennai. I'm studying chemical engineering at Anna University, and
okay.
I'm going to be writing GATE in 2023 February. So I'm
Okay.
expecting what will be the current topics, and I'm expecting some questions in this session. Thank you.
Okay. So what about you, Anand and Samuel? You can write it in chat box also.
Yes, sir. Sir, I am Anand Rodi from Maharashtra. I am studying chemical engineering from MIT Alandi, which is located in Alandi, place of Maharashtra. Yes, sir. I am in third year of chemical engineering, BTech chemical.
Oh, okay. That's good.
Hello, sir. Hello, sir. I'm Samuel from Chennai, sir. I'm doing my BTech third year in chemical engineering at St. Joseph College, Chennai, sir.
Okay.
So I would like to know the important concepts that we could follow, we could cover to crack GATE 2023.
Anyone else? Okay. So basically, we will be looking into the past year questions, and from that you can get an idea. So what all kind of questions can you expect in the coming GATE exam? And also I see that most of you are from third year, so we will be covering the concepts concepts in more detail from the next videos. So for today, I think I will start with the presentation. If you have any doubt, you can unmute yourself and just speak up. So I hope my slides are visible to all. If they are not, you can just speak up. So our main aim of this session will be, per session we will be taking at max 4 to 5 questions. We will be solving those questions in detail in this. Okay, so today I have just taken 4 of the questions from heat transfer from GATE 2007 paper. So this past year GATE paper, you can get it from our GATE portal. There you can find the previous year question papers. Yes, so today I have taken this question number 41, 42, 43, 44, and each of those are from the heat transfer paper. Chemical engineering paper, and the subject is heat transfer. So if you want to know more about the topic that has been covered in this question, I have also provided 2 links related to the NPTEL course. So one link would be the web course and the other link would be the video course. So for in-depth analysis of that question, you can visit this link and see the concept related to that question. Okay, so we can start with the question. So the first question is, for the 2 long concentric cylinders with surface area A1 A2, the view factor F22 is given by. Okay, so has anyone, I think you would have covered this heat view factor in the radiation part of the heat transfer subject. So if anyone wants to discuss more about this question, then they can speak up. So does anyone over you knows what view factor is? Okay. So I will just play the video solutions that we have prepared, and then we can take a look into another question. See what type of question. Okay, so let's just start the solution of the first question. Hello everyone. So today we will be solving the question number 47 from GATE 2007 chemical engineering paper from the subject of heat transfer. So I will be reading the question. The question is, for the 2 long concentric cylinders with surface area A1 and A2, the view factor F22 is given by, and we are given the option. So this is an MCQ type of question. So in this question, we have been asked to find the view factor for the given surfaces as shown in the figure. So this topic of radiation and view factor is covered in this NPTEL web as well as course video, and you can find the link and look into them for more details. So let's just look what is view factor. So in order to find radiative heat exchange between multiple bodies, we define the view factor as given by these 3 terms. So let's say if I'm having 2 objects F1 and 2 objects 1 and 2. Okay. So this is my first object, this is my second object, and this side will be my reflecting surface, and in this case this is my reflecting surface. So my F12 will be defined as fraction of energy that leaves the surface 1 which reaches surface 2. That is my F12, and fraction of energy that leaves the surface 2 which reaches surface 1 is F21. So in general we can write it as Fmn, in which the fraction of energy, which is the fraction of energy leaving surface m which reaches surface n. So this is how we define the view factor. Okay, so in this question we have been asked that for the given symmetry what is F22. Okay, so from thus we can say that the energy leaving surface 1 and arriving at surface 2 is given by this term. So here EB is just an energy emitted by the surface, and similarly the energy leaving the surface 2 is given by this term. So all the incident radiation will be absorbed by the black body, and the net energy exchange is given by this term. So and at a thermal equilibrium between the surfaces, this Q will be equal to 0, and if EB1 is equal to EB2, then we get this correlation, and by solving this we can get A1 F12 is equal to A2 F21. So these equations will be useful, and this is known as reciprocity law or theorem, whatever you want to call it. One more equation that we need to remember is the relationship between the view factors. So yes, so the another property of the shape factor or the view factor is that when the surface is enclosed, then the following relation holds true. So let's say if I'm having two objects, 1 and 2 surfaces, then in that case I can write it as F11 plus F12 is equal to 1. Also F21 plus F22 equal to 1. So this will hold true. Okay, so using those concepts, we will be solving our equation. We will be solving the question. Okay, so here we have been given for the two long concentric cylinders with surface areas A1 and A2, the view factor F22 is given by. We have to find F22. Okay, so from the first law we can write it as F11 plus F12 is equal to 1. Also we can get F21 plus F22 equal to 1. The other thing that we can write is from the reciprocity theorem, A1 F12 is equal to A2 F21. So we shall be using these three equations to find the final answer. So the first term that we want to find is F11. So from here we can see that the reflecting surface of the first object is this outer boundary. So if my radiation is leaving from this surface, then it won't come back ever to this surface. So the energy won't be coming back to this surface, and hence we can say that F11 will be 0. And that will give us F21 is equal to 1. And now using the reciprocity theorem, we can say that A1 into 1 is equal to A2 into F21. That will give us F21 is equal to A1 upon A2. Now from this we know that F21 plus F22 is equal to 1, and F21 we have found it out as A1 upon A2 plus F22 is equal to 1. That means F22 will be 1 upon A1, 1 minus of A1 upon A2. So this is my final answer. So yes, this final solution, you can see that for the given question, it will be 1 minus A1 upon A2. Okay, so we looked at the solution. Hello everyone. So today we will be solving the question number. Okay, so we just look at the solution of this question number 41 from GATE 2007 paper. I hope you have understand it, and if you have any doubt, then you can ask it and we can solve it again. Or else we can move to the next question.
So can you say how F11 was 0? I cannot hear it properly on the video.
Okay. So let me just show it to you. So let's say here we have to find F11. Okay. So what is that? Fraction of energy leaving 1 and incident on 1. Okay. Now if you had seen from our geometry, so we had given this was our first and this was our second surface. Okay. And here the outside part was reflecting 1. Okay. So if I just consider my first surface 1, okay, so this is my reflecting surface. So if I have an energy that is leaving 1, so it won't ever come back to this surface again. So that is why we write it as F11 equal to 0. Okay, but in case of second, let's say if my reflecting surface was the outer one. Okay, so if my energy surface is leaving from here, it will come and again reflect it from this own surface, and it will reach the same surface. So the energy leaving from this surface, that is we are taking it as 1, it will reflect back and again it will again incident on this surface 1. So if the outer surface has been coated and the inner surface is reflecting, then in this case F11 won't be equal to 0. So in this specific question, this outer surface was reflecting, hence the radiations which have left this first surface won't be coming back to again this surface if we had only considered this object. Okay, so that is why we are taking it F11 as 0, whereas for the second object the outer surface was coated and the inner surface is reflective, and that means that F22 was not equal to 0. So while calculating this F1 and F2, you have to just consider this specific surface or object.
Yes, I got it, sir. Thank you.
So we can take a look at the second question. So this question is from the initial chapters of the heat transfer, in which you are calculating this steady state heat conduction. Hello everyone. We will be solving question number 42 of the Chemical Engineering GATE 2007 paper, and the subject is from the heat transfer. The question is, the composite wall of an oven consists. I can try. Of three material A, B, and C under the steady state operating conditions. The outer surface of the temperature TSO is 20 degrees Celsius. The inner surface of the temperature is 600 degrees Celsius, and the oven air temperature is 800 degrees Celsius. For the following data, the thermal conductivity Ka is equal to 20 and Kc equal to 50, thickness La equal to 0.3 meter, Lb equal to 0.15 meter, and Lc equal to 0.15 meter. inner wall heat transfer coefficient H equal to 25 watt per meter square Kelvin. The thermal conductivity Kb of the material is calculated as. So for the given system, we are given a few properties and we have been asked to find the thermal conductivity Kb. And this is the MCQ type of question. The lecture notes and the course video, you can find it from these references. Okay, so let's look at few of the basic concepts that will be helpful to solve this question. Okay. So let's say if I am having a wall, this is my wall and this is my x direction, and let's say the temperature over here is T1, T2, and here everywhere it is T infinity. Okay, so if I have to find the conduction, Q conduction across the wall, then we can write it as minus of Ka del T by del X. Now we can simplify this to write it as delta T is equal to delta X upon Ka. Now this entire term we can call it as resistance. So basically this heat transfer rate is directly proportional to the temperature gradient, and there are this proportionality constant. So we can also write it as the heat transfer rate is equal to the temperature difference upon the resistance that it faces. So we can write it as delta T upon R. Now again, if there are multiple walls, let's say L1, L2, L3, then correspondingly we'll be having R1, R2, R3, and there will be T1 and T2. So we can also write it as delta T upon R1 is R2 plus R3. Again, if I want to find Q convection, so here I was having my air. So the convection heat rate from the wall, from the surface of the wall to air is given as Q is equal to H A T infinity minus the any surface that we are considering. Okay. And in this case, this convection and conduction will be equal since the heat transfer is happening across the surface. So here we can also write Q conduction is equal to Q convection. Okay, so we'll be using this basic concept to solve the question that we were discussing earlier. Okay, so again we'll start from the scratch. The composite wall of an oven consists of three materials A, B, and C. This is A, B, and C. The outer surface temperature is given as 20 degrees Celsius, and the inner surface temperature is TSI we are given as 600 degrees Celsius, and T infinity we have been given as 800 degrees Celsius. Now LA, now we are given thermal conductivity, so Ka, Kb, Kc equal to 20, Kb we have to find, and Kc is 50. We have been given the length 0.3, 0.15, and 0.15. Now one more information, the heat transfer coefficient we have been given as 25 watt per meter square, and we have to find the thermal conductivity of material B. So yes, so we can write Q convection is equal to Q conduction for this entire system. We can write it as the area term will cancel out for this. So it will become h of T infinity minus of T surface is equal to delta T upon, now in this case we will be having three resistances corresponding to each of those wall boundaries. LA upon KA plus LB upon KB now we have to find this term. Okay, so we will just straightforward put up those values that we are having. 25 minus 800 minus 600. Since we are calculating the difference, we need not convert them into Kelvin. We can keep it in Celsius. Now for conduction, this delta T will be across my entire wall boundary. So this will be equal to 600 minus of 20. -600 20 upon LA, we have been given it as 0.3 on KA 20 plus okay, so this you can write as 25 minus of 200, that will give us 5000 is equal to 580 plus 20 into 5 is 100, so this will become 0.015 plus 0.15 upon kV plus this will become 0.003. So you can solve this equation, and from here you can find the value of thermal conductivity of B as 1.53. You must check all those you need to check for any unit consistency, and the thermal conductivity we have to find it as watt per meter square, so that you need to check for each of these cases. Okay, so the final answer is 1.53 watt per meter Kelvin. So from the given options, we can select this final answer 1.53 watt per meter Kelvin. Okay, so we can move on to next question. If you have any doubt, then you can again ask it.
So how Q conduction equal to Q convection? Can you elaborate the reason?
So the total net energy change of any system that we are considering will always be equal to 0. Okay, so in this case, if you will consider, so the heat so here so this is my entire system that I am considering. Okay, so here I am having T infinity, here also I am having T infinity. So the heat change across this part will be equal to my heat change across this entire wall, and this will also be equal to this thing. So that is why we are equating this heat exchange across this part. So here we are having air and heat will be exchanged through this surface. So that is my convection. Okay, convection, and here the entire it will occur conduction across the wall. So that is why I'm equating both. This convection is equal to conduction.
Thank you, sir.
So now we look into the third question. Hello everyone. We will be solving question number 43 from GATE Chemical Engineering paper from 2007, and the subject is heat transfer. The question is, water enters a thin walled tube. We have been given the dimensions of the tube. Length is equal to 1 meter and diameter equal to 3 mm at an inlet temperature of 97 degrees Celsius and mass flow rate of 0.015 kg per second. The tube wall is maintained at constant temperature of 27 degrees Celsius. Given the following data for water density, that is rho is equal to 1000 kg per meter cube, viscosity we have been given, specific heat we have been given as 4184 joule per kg per Kelvin. Inside heat transfer coefficient is given as H is equal to 1298 watt per meter square Kelvin. The outlet temperature of water in degrees Celsius is that we have to find. And this is a multiple MCQ type of question. Okay, so from reading the question from the ones, we can see that there is a tube and the flow of water is happening through it, and we have to find the outlet temperature of the water that is passing through it. Okay, so this is my tube. Length is equal to 1 meter, diameter is equal to 3 mm. Now water is passing through this tube with an inlet temperature of 97 degrees Celsius and mass flow rate of 0.015 kg per second. The tube is maintained at a surface temperature of 27 degrees Celsius. 27 degrees Celsius. And we have been given a few of the properties. Rho is equal to 1000 kg per meter cube. Viscosity is equal to 489 10 raised to minus 6 Newton second per meter square. Specific heat given it as 4184 joule per kg Kelvin, and the inside heat transfer coefficient H given as 12978. Okay, and the outlet temperature we have to find. So let's just draw the temperature profile for this system. A rough temperature profile. So here, this is my temperature of the surface. It is 27 degrees Celsius. The inlet water temperature is given as Ti is equal to 97 degrees Celsius, and it will decrease, and we have to find T out is equal to question mark. So here you can see that the change in temperature, that is delta T, is not following a linear trend. It won't follow a linear trend since the flow is happening across the cylinder, and hence we need to find the log mean temperature difference. So here you can say delta T1 will be higher than the end temperature, that is delta T2. Okay, so let's just find LMTD. So this log mean temperature difference will be our driving force due to which heat exchange is happening. Delta T1 minus delta T2. So this first delta T1 will be 97 minus of 27. That is 70 minus T2 is T0 minus of 27. T0 minus of 27 in bracket 1 ln of 70 T0 minus 27. So this will come around as 97 minus of T0 upon ln of 70 minus So this is my login temperature reference. I will be using this to find my heat exchange. So for this given tube, we have given mass flow rate. Here there was a heat transfer coefficient. So we can write the heat balance as m dot Cp delta T is equal to U A LMTD. The mass flow rate we have been given as 0.015 kg per second. Cp we have been given as joule per kg per Kelvin, 4184. That delta T will be change in temperature across inlet and outlet. Okay, so here it will be 97 minus T naught. U is my overall heat transfer coefficient. So here we have been given the inside heat transfer coefficient as 12978. And that we can write it as 12978 into area. So the heat exchange will be happening across the surface of this cylinder. So the area will be pi dl. Okay, area will be pi dl. That will be 3.14 into the diameter is 3 mm. So that we can 3 mm, we can write it as 0.003 meter. The length is 1 meter. So this will somewhere come around as 9.42 into 10 raised to minus 3 meters square. This will be using over here. The LMTD from the previous slide was this 97 minus T naught. T naught upon ln of okay. So we can cancel this 97 minus T naught and just solve this. You can write this log term as this. You can write it as 70 upon T naught minus 27 is equal to e raised to 122.319 upon 62.76. That will somewhat come around as e raised to 1.949 is equal to 7.02. So this will be 70 upon 7.02 is equal to 9.97. That implies T naught will be 27 plus 9.97. That we can write it as 37. So the final outlet temperature from this tube is 37 degrees Celsius. From the given options, we can select the final answer as 37 degrees Celsius. Okay, so we have looked upon the third question that was related to heat transfer happening in the fluid which is flowing through a tube and in which the tube was kept at the constant temperature. Okay, so do you have any doubts regarding this question 43? Okay, so we can move on to the last question for today's session. So this is also more or less similar to our previous question. Hello everyone, we will be solving question number 44 of GATE Chemical Engineering paper from 2007 from the subject of heat transfer. The question is, a hot fluid entering a well-stirred vessel is cooled by feeding cold water through a jacket around the vessel. Assume the jacket is well mixed. For the following data, mass flow rate of hot fluid is 25 kg, 0.25 kg per second. Mass flow rate of cold water is 0.4 kg per second. Specific heat of oil is 6000 joule per kg Kelvin. Specific heat of cold water is 4184 joule per kg Kelvin. The inlet and exit temperature of hot fluid is given as 150 degrees Celsius and 100 degrees Celsius respectively. Inlet temperature of cold water is 20 degrees Celsius. The overall heat transfer coefficient is given as 500 watt per meter square. We have been asked to find the heat transfer in meter square. So let's just draw a schematic of the system. So we have been given a well stirred vessel. And the hot fluid is entering TH in, and it is a well stirred vessel. So let's just write all our assumptions over here. First is well stirred vessel, and it is cooled by feeding cold water through a jacket around the vessel. The jacket is also well mixed. The mass flow rate of the hot fluid, we have been given m dot h, and the mass flow rate of cold water. Let's assume the cold water will come from here, and the exit is this Tc out, this temperature. Similarly, the outlet of the hot fluid is Th out. And we have been given m dot h, mass flow rate of cold water m dot c, specific heats of oil Cp, specific heat of cold water Cpc, Cph, the inlet and exit temperature of hot fluid. Okay, Th input is given as 150 degrees Celsius, Th out is given as 100 degrees Celsius, Tc in is 20 degrees Celsius, Tc out we haven't been given. The overall heat transfer coefficient is 500 watt per meter square Kelvin, and heat transfer area we have been asked to find out. Okay, so here we have been given it is a well stirred vessel. So the temperature across the entire vessel will be, we can say that it will be equal to the outlet of the temperature of the outlet of the fluid. Similarly, for the jacket, we can write it as, since it is also well mixed, TC output. Okay, now we need to find the heat balance across this system. So this change of heat for this cold fluid will be equal to change of fluid across the hot fluid, and this will be equal to the change of heat across the vessel. Okay, so let's just consider the first two terms and solve it. So for the coolant, we have m dot cpc. It will be Tc out minus of Tc in is equal to m dot cph. We need to take a look into the direction of heat exchange. Based on that, we can write it as coolant outlet minus coolant inlet, and similarly it will be hot fluid inlet minus of hot fluid outlet. So yes, we can put these values. The mass flow rate of the coolant is given as 0.4 kg and the specific heat is given as 4184. You can use these two values over here. 0.4 into 4184. Tc out, we don't know, and the inlet is 20 degrees Celsius. For the hot fluid, we have been given as the hot flow rate is 125 kg per second and the specific heat is 6000 joule per kg Kelvin. The hot fluid inlet temperature is given as 150 degrees Celsius and the outlet is 100 degrees Celsius. Okay, so here we have made a mistake. Here it should be TH outlet minus of TH inlet. 150 minus of 100. We can solve this to find Tc out minus 20 is equal to, let's just calculate this, 0.25 into 6000 into 50 will give us 75,000 upon 4 into 4184, 1673. It will come around as 44.81. So this will give us as Tc out is equal to 20 plus 44.81, that will be 64.81 degrees Celsius. Now we had to find this heat transfer area in meter square. It is A is equal to question mark. Now again, this heat exchange across the both of these fluid is occurring across the vessel through the jacket. So that is, we can write it as QC is equal to QH is equal to Q of vessel. So let's just consider, for the time being, we are considering the heat balance of this hot fluid. So that is 0.25 into 6000 into 150 minus 100 will be 50 to heat exchange across the vessel will be UA delta T. Since the vessel was well stirred and well mixed, this delta T will be equal to this delta T will be equal to the temperature of vessel minus of temperature of jacket. Okay, so this delta T is basically the heat exchange across over here. So here it was T vessel and this was T jacket. So this T vessel will be equal to the outlet temperature and this T jacket will be equal to the outlet temperature of the coolant. Okay, so this delta T will be T vessel minus of T jacket. Okay, that implies this LHS will be equal to 75,000. The overall heat transfer area, heat transfer coefficient has been given it as 500 watt per meter square Kelvin into area into delta T. We have to find the temperature of vessel. So this temperature of vessel we had, I think it is given to us as the outlet of hot fluid. It will be 100 degrees Celsius minus the temperature of jacket outlet will be 64.821. Okay, so we can solve this. This area is equal to 75,000 upon 500 given 150 upon 100 minus of 64.81. So it will give the area as 4.26 meters square. So the final heat transfer area that we were asked to find is 4.26 meters square. Yes, the correct answer is option D. It is 4.26 meters square. Okay, so do you have any doubt in this question? The last one. I guess that's a no. So today we looked upon 4 questions from the heat transfer, and videos of this will be available shortly on the NPTEL portal. So in the next time we will try to make this lecture a bit more interactive with more questions that the participants can answer to. What else? Yes, so next time also I think I will be going with this heat transfer subject only, and I will be solving questions from another year. So this is the first time that we are carrying out this live sessions of solving this GATE question papers. So we expect that more participants will be joining us soon in the subsequent sessions. So if you have any doubts, you can always contact us through this session, or else I can provide you my email ID also. Okay, so do you have any doubts, both of you?
Sir, email ID, sir.
Just wait a minute. I will write the email ID in the chat box. So I have mentioned it in the chat box. It's Rahul nptel25@gmail.com. So if you have any question related to this GATE previous year questions related to any subject or some basic concepts also, then we can discuss it in the next session.
Okay, sir. Thank you, sir.
Okay, thank you. Bye.